All right. Looks like we're at the top of the hour, so we're going to get started. Hi, everybody. Welcome to Webinar Wednesday. If you are here to learn about simplified XRF principles and how XRF is used in different industries, then congrats, you've come to the right place. I'm Lauren Armstrong, Marketing Director for Quantum Analytics, and I'll be moderating today's event. Today, I'm very excited to be joined by Brian Diverse, Spectroscopy Product Manager for Quantum Analytics. Brian brings a great perspective to this topic because of the different hats he's worn over the years. Everything from sales and application support, method development, and customer service. He's one of those people that can explain highly technical concepts to your everyday product user, which makes him a fantastic presenter for today's topic, simplifying XRF for the modern user. Before I hand the mic over to Brian, if you have any questions, please enter them into the questions module at the right side of the screen. And if we don't get to them today, Brian will certainly answer them and send you an email after the webinar. Well, I think it's time to simplify XRF. So Brian, take it away.
Outstanding. Hey, thanks, Lauren. I appreciate that wonderful intro here. And thanks, everybody. I'm really glad that you all joined me today. It's really impressed by the number of people that have showed up. So this must be a very interesting topic. I hope that you guys get as much use and enjoyment out of it as I do giving it. So yeah, this is an exciting time for me, and I just want to get involved and get to know you guys a little bit better and how we might be able to help you. And so let me get you started here and get you a little bit more information about who we are, Quantum Analytics. We're a value-added distributor of multi-vendor analytical instruments. We have everything from chromatography and mass spec to spectroscopy and even sample preparation instrumentation and a little bit more too. So we've been doing business for about 30 years now, and we're headquartered in Foster City, California, but we also have a tech center located in Houston, Texas, which is where I'm calling in from. So our keys to success is our ability to provide rental, leasing, and financing programs for companies ranging from, early startup labs to even Fortune 500 companies. We provide cross-platform system integration. We do installation. We provide training for on-site and even large group training sessions at our different locations. We do application development, and we also provide product support. We do maintain a multi-million-dollar inventory of new and refurbished instrumentation that's available for immediate delivery. So as for me, Brian Diverse, your speaker here, I've been working with spectroscopy for about 20 years now, both as customer support and technical sales and application roles. I've been working on everything from X-ray to infrared to near infrared, Raman spectroscopy, and even some NMR spectroscopy. And after all these years, I'm still very much a student of these technologies, and I learn more and more every time I work with one of you and get involved with your applications. I'm extremely grateful to work with so many wonderful and interesting people like yourselves, and I am delighted to be here and talk with you today. So let's dive into our discussion about simplifying XRF. This technology, here's the whole reason for my webinar. This technology has made us able to do a lot more while understanding less about, excuse me, less about why we're doing, what we're doing, and has increased our dependence on others. Individually, we depend more on technology than ever before, but we can do much more than ever before. So collectively, technology has made us smarter, more capable, and more productive. But what technology has not really done has made us wiser, right? So let's take a moment to just take a deeper dive into some of the lab equipment that we use today. Like we're going to focus on XRF, X-ray fluorescence spectrometry, which is widely used. It's a non-destructive analytical technique that can help you obtain elemental information from different types of materials, all sorts of different types of materials. Popular uses of XRF can be found in cement, metals, minerals, oil and gas, environmental, and even food applications. Virtually, virtually any lab with the right expertise can make use of it. However, most modern everyday users of XRF miss out on how it works or even why they should care. In this webinar, you will learn simplified XRF principles and obtain a better understanding of what this information can provide you with. So here we'll cover some basic principles about XRF. You'll learn about modern laboratory XRF technology. We'll dive into a few applications where XRF has been effective, and then conclude with some things to consider regarding XRF technology. So we'll start with principles of XRF. X-rays are another part of the electromagnetic spectrum, of which you'll see like radio waves, microwaves, what we all call visible light. X-rays fall between gamma rays and ultraviolet rays on that spectrum. Apart from the wave properties, light also has properties of particles. This is expressed by the term photon. And here we will be using the term photons or X-ray photons in this discussion, right? So the thing to think about this radiation is it's the intensity. It's the number of the photons that are emitted or measured per unit of time. We will use the number of X-ray photons measured per second. So you'll see sometimes counts per second or CPS as the unit of intensity. But don't worry about that right now. We'll come back to that in a bit. XRF, or let me back up. Let's talk about the origins really of X-rays, right? So X-rays are super powerful. There's a lot of energy, so they can pass through things, which is key if you want to check out your bones inside your body or from the outside of your body, right? Consider this, right? Different atoms have different atomic weights. So really high energy, high atomic weight, very dense atom is going to be able to absorb a lot of energy. Smaller atoms that maybe are looser and have lower atomic weight are going to get kicked around by any old photon that wants to come along. Have you ever noticed that when you have an X-ray, if any of you have ever seen an X-ray, everybody's seen an X-ray, right? If they've broken a bone or whatever. But if you've ever really looked into your X-rays here, you'll notice that you'll see your bones, but like the rest is just some sort of this grayish black mess. Well, that's because your soft tissue has smaller atoms. Your bones, like the calcium atoms in your bones, are much larger. So they're going to absorb the X-ray photons. So what is XRF? The definition: X-ray fluorescence, XRF, occurs when fluorescent or secondary X-ray is emitted from a sample that is being excited by a primary X-ray source. XRF analysis is a method to do qualitative and quantitative analysis of elemental composition by excitation of atoms and detection of their tongue-tied here, characteristic X-rays. So basically, XRF is a non-destructive analytical technique used to determine chemical composition. Now, you guys know that you should never trust an atom, right? They make up everything. I know, it's my corny jokes. There's a couple in them, I gotta warn you. Anyway, let's take a minute just to pause and talk about chemical elements, because it's an important part of this discussion. And it's basics, but here we go. So chemical element is the simplest form of matter in that it cannot be further broken down using chemical means. The term element may be used to describe atoms with a given number of photons or any amount of pure substance made up of atoms of one element. The number of protons, particles in the atom's nucleus, right? This determines the element. Elements on the periodic table are arranged in order of increasing numbers of protons. The number of protons is also known as the element's atomic number, right? So presently there are, well, we know about 118 known elements, ranging from natural and man-made elements, right? And in regards to X-ray fluorescence, the elemental range is from beryllium to uranium, or 4 to 92, if you like to use the numbers. Each of these elements present in the sample produces a unique set of characteristic X-rays that is very similar to like a fingerprint for that very specific element. So we're going to get into a bit of the principles here. And so what you'll see in the center of the atom, right, is that nucleus. It's made up of protons and neutrons. We talked about that. Each proton carries a positive electrical charge, but the neutrons carry no electric charge. So the nucleus of the atom is positively charged because of its protons. Electrons are particles that orbit the nucleus at high speed and carry a negative charge, which balances the positive electrical charge of the protons in the nucleus. Since the total negative charge of the electrons is equal to the positive charge of the nucleus, an atom is neutral. The negative electrons are attracted to the positive protons, so electrons stay around the nucleus in discrete shells. So you think about this, you got the electrons that reside in these discrete shells. This is kind of the key or an emphasis for XRF, that these shells are labeled K, L, M, and from inner to outer. And X-rays will typically affect the inner shells, usually around the K and L electrons. Oh, sorry. Okay, so a sample is irradiated with high energy X-rays from a controlled X-ray tube, right? This is your steps, if you will, on what happens in an XRF absorption, right? So you have primary or incident proton that comes in. When an atom in the sample is struck with an X-ray of enough energy, so greater than the atom's K or L shell that's their binding energy, an electron from the atom's inner orbital shell is dislodged. The atom then regains stability, filling the vacancy that's left in the inner orbital shell with an electron from one that's from the atom's higher energy orbital shell. Electron will drop to the lower energy state by releasing a fluorescent X-ray. So this energy that the X-ray is equal to is equal to the specific difference in the energy between two quantum states of the electron. This measurement of this energy, this is the basis for XRF analysis. This is the key component. So here, let's look at an example, right? This is the tungsten material. The K shell is the binding energy, and it equals 69.5 keV, kilo electron volts, right? And the L shell binding energy equals 10.2. If the electron falls L to K shell, then the X-ray that's emitted is 59.3. You guys see the math? Yeah. So if you look at a sample, right, each element that is present in a sample produces a set of characteristic X-rays that is unique for that very specific element. Therefore, this is the basis, right? XRF spectroscopy is especially useful for this type of elemental analysis. And if we look at the spectra, what does it look like spectroscopically? Like this, it is the fingerprint. It is illustrated by examining the energy spectrum and its scattering peaks. When X-ray energy causes electrons to transfer in and out of these shell levels, XRF peaks with varying intensities are created and will be present in the spectrum. So if you look along the X and Y axis here, the peak energy identifies the element, right? So this is your X axis, and the peak height or the intensity is indicative to the concentration. So when you see various elements, they have their very specific position on the x-axis, and the intensity will basically give you some information about the concentration of that material that's present, or that element that's present. So XRF energies, like if you look at some species or types of elements, like organic elements like hydrogen, carbon, nitrogen, oxygen, they're very low energy elements, and some are too low for some conventional XRF detectors. And you have low energy elements like chlorine, argon, potassium, calcium. This gives you the K lines, and the L peaks from these elements are just too low in energy. High energy elements like barium, mercury, lead, uranium, these give L lines. The K peaks from these elements are too high in energy. And then the middle energy elements are like rhodium all the way to iodine, and they may give you information in both K and L lines. And there's a useful guide that you guys may want to refer to. It's pretty handy. I like to use it. It's this X-ray data book that you can refer to. I think I have the link here. That you can sort out which lines to consider for your specific analyte of interest. Here you can see an example of where you would see the K line for sodium. So when you're talking about XRF, there's some other anomalies that are happening atomically, right? And so there's some artifact peaks that can come from different sources, and here we'll talk about some of the scattering effects that you'll see. So scattering occurs when incoming X-rays do not produce fluorescence, but rather they collide with the atoms of a sample, which results in a charge in the direction of motion of a particle. So a couple to consider, a few scattering terms. There's the Rayleigh scattering. This is the interaction with electron or whole atom in which no energy is exchanged. An incident X-ray energy equals scattered X-ray energy with smaller angle change in direction. This, you may have heard, is also called the elastic scattering. And then if you look at Compton scattering, these are interactions where they occur with essentially unbound electrons, with transfer of energy shared between recoil electron and scattered photon. This is also called inelastic scattering. And then you have this great word, I love to say it, Bremsstrahlung, right? Or continuum radiation. This is a German term for breaking radiation, and it appears in spectra as very broad peaks due to backscattering of X-rays from the sample to detector. This is more prominent. You'll see this more and more in XRF spectra with samples that are less dense, right? So kind of give you an example, what does that look like spectroscopically? When you look at the spectra of this, let's look at some of these effects, right? So Rayleigh scattering, here we see elastic scattering from a metal alloy sample, right? Now remember, this is the interaction with the electron or whole atom in which no energy is exchanged. The peaks are arising from the target anode in the X-ray tube source. Here in this case, it's using a rhodium source. This may appear in all of the XRF spectra that's acquired on the instrument, right? So they'll be consistent. This is typically observed in spectra in dense samples as weak peaks, right? So that's why you see them so small here. When you talk about my mistake. When you talk about Compton scattering, here we see inelastic scattering from like a cellulose sample, right? Remember, this is where interactions occur with essentially unbound electrons with the transfer of energy shared between the recoil electron and the scattered photon. This is typically observed in spectra of low density samples as fairly intense peaks, right? This is a pretty significant peak that we're seeing. Bremsstrahlung, right, our continuum radiation. Remember, this is in the spectra as a very broad peak. Could you see this broad, looks like almost a real rounded kind of a peak, right? And this is due to the backscattering of the X-rays from the sample to the detector. This is more prominent in XRF spectra of less dense samples. So before we were looking at artifacts from like the tube, right, from the radiation process. Now we're looking at artifacts from the detection process. Here we'll talk about terms like some peaks and escape peaks, right? Some peaks are, they're two photons, they strike the detector at the same time. The fluorescence is captured by the detector, recognized as one photon, twice its normal energy, right? So a peak appears in as spectra, but at 2 times the element's energy. So if we look at a sum peak, or the like in this example here, we have some titanium foil that was measured, and you look at 2 peaks, 2 titanium photons that struck the detector. We got a peak at 9.02, and if you look at this energy, it's 4.51 plus 4.51, giving us that anomaly. Now, an escape peak, this is an artifact. It's an artifact peak that appears because of the absorption of some of the energy of the photon by the silicon atoms in the detector, right? So the detector itself is made of silicon, and when you have a combination of these of your material, your element that you're analyzing, and you have that with some of that's absorbed by the silicon, now you're doing like a deduction, right? This is a sum peak. And so, I'm sorry, an escape peak that you now do a subtraction, right? So you take your titanium minus your silicon. So if the peak is located at 2.77, you'll see that if we take the position for titanium at 4.51 keV and subtract that by 1.74 keV, you actually will get this peak that you'll see at 2.77 keV. So why do I bring this up? Really just to give you some details about some things that you just need to be aware of, right? So are you confused yet? Well, don't worry, okay? So the good news here, guys, is that most modern XRF technology, it has very clever software, and this will help you sort through all of this information. What's important for everybody here to know is just take the time to understand what your XRF results mean. So learn some of the tips and the tricks that are especially important with like sample prep, right? You can use this to try to avoid some of the pitfalls that may skew your results. So speaking of tips and tricks, right? So let's look at some of the effects that you need to take into consideration. Environmental effects is one that really is sample dependent, right? You really need to consider what types of samples you're running, right? So if you look at light, if you're trying to analyze light elements like sodium to chlorine, these emit weak X-rays, especially attenuated by air. Good news for you is that there is a solution. You can purge the instrument with helium or nitrogen, which is less dense than air and attenuates less. Remember, X-ray technology, X-ray XRF technology is very sensitive, but you can create this environmental chamber, if you will, and reduce some of those environmental effects. So you can also do that by evacuating air from the sample chamber itself by using a vacuum pump. And in some cases, you can even apply both. There's sample effects. Now, this is important to consider when you're prepping your sample, right? So if you think about your sample, what you're trying to analyze, look at the surface of the materials being analyzed, and is it not representative of the entire sample, right? So look at things like particle size, inhomogeneity, surface contamination, things like that. XRF is a surface analysis technique, so inhomogeneity and contamination will skew some of your results. I put up this graph here so you can kind of see how there's a correlation between sample prep efforts and cost of some of these efforts, but how the quality of your results will improve with a little bit more effort you put into your sample preparation. So XRF lends itself to versatile sample forms. That's one of the beauties of XRF. You can use pressed pellets, fused beads, solid samples, loose powders, liquids, films, slurries, you name it. You can analyze it by XRF. For powders, grinding can minimize scatter effects due to some of the particle size that you have, right? So anything like a 400 mesh is possible. So, you know, things like grinding, it can ensure that your measurement is more representative to the entire sample versus the surface of the sample. You can do a pressing like hydraulically or manually. There's these presses that you can use that compacts the sample more into the analysis area and ensures that you have uniform density and you get better reproducibility. So that's really, really helpful, especially when you're working with these powders. You know, the more sample prep you can put into it, like some of the pictures you'll see here, how they'll press these pellets of powders. And you don't have to spend a lot of money on some of these sample prep techniques, but they do have, the more you spend, usually the better they get. But it also, you got to consider some other considerations on, you know, how fast of the analysis do you need, how accurate of the analysis you need, and so on. But I digress here. So solids, right? So for solids, you orient the surface patterns in the same manner so you minimize the scattering effects. So polishing surfaces will also minimize scatter effects. Flat samples are optimal for quantitative results. And for liquids, these samples should be fresh when analyzed, right? So you don't want them sitting around for a very long time, and you want to be able to try to minimize your analysis time to the most effective timing, or I should say most efficient timing, especially with samples that tend to evaporate. Samples should not stratify during analysis. Samples should not contain precipitants or solids, and analysis should show this analysis could show settling trends with time, right? So another thing I'll say about liquids and even some powders, if you're going to run them as loose powders, you should pay attention to the films that you use, because you want to be able to use the right films for the right material. And if you're not familiar with what films you should be using, there are a number of resources that are available to you that can help you, especially there's a number of companies that make these types of films, and they have their own guidelines that tell you which ones are good for the types of products, which type of samples you're going to be analyzing, the thicknesses that you might need to use, and so on. So XRF capabilities, you have effectively like 3 modes of operation, more like 2.5, right? So for qualitative analysis, this is your identification of X-ray emission lines, which nowadays is usually fully automated, but no one really should take this program results as absolutely correct, right? So when you analyze your sample by XRF and you get qualitative information saying, aha, it is this element, or these elements are present, they're usually pretty good, but again, look at it with a cautious eye, just to make sure that does make sense. When you think about being able to determine concentration, right? Quantitative analysis, you want to know how much is inside. This is the theoretical background and the corresponding calculation steps that are done in both types of techniques that we'll get into with energy dispersive and wavelength dispersive. But there are differences between these calculation approaches. And so you can do this with primarily a calibration curves, right? So you're using you're using standards to create a curve. And then if you think about a semi-quantitative analysis, right, this is an estimation of concentration, just about how much is in there. This is kind of somewhere between qualitative and quantitative. You're able to quantify elements from sodium to uranium. There's no need for some dedicated calibration curve. Any sample type, like a pressed pellet, loose powder, fused bead, solids, anything like this can be run. With a little bit of caution here, I'll say it can operate somewhat like a black box, right? And it does, what you see though is what you get, right? And it allows for you to interactively evaluate your data. But think of it as giving you some ballpark figures, right? So we say semi-quantitative, meaning approximate information. So how do we calibrate that, right? For empirical calibrations, the user must first analyze known samples to obtain the count intensity, which is then plotted using an offline software to generate the calibration curve. The curve data is then put back onto the analyzer, which is then be run to give immediate results, right? So you scan certified reference materials or standard reference materials that you get that have known concentrations, and these could be reference materials that you've analyzed yourself from some other technique, or you are using a third-party certified reference material. And now, empirical testing modes are only suited for measuring samples for which chemical compositions fall within the narrow calibration range. And interferences like spectral and matrix must be taken into consideration within the calibration. So the method is the most accurate and widely used in process control where similar well-known reference samples are available, right? So again, if you are using a third-party reference material, be cautious or consider the matrix that sample's made up of, right? And make sure you take that into account. You want to compare like to like samples. This will give you much better accuracy. Now, fundamental parameters is one of the major advantages of XRF because it allows for fast and easy determination of chemical composition without performing a calibration. Right? So for measuring samples of unknown chemical composition in which concentrations of light and heavy elements may vary from parts per million up to high percent levels, fundamental parameters, or you may have heard of as an FP analysis, is used to simultaneously compensate for a wide variety of geometric effects, right? So this is including small and odd shaped samples, plus X-ray absorption and enhancement effects, as well as spectral overlaps are included in this equation. An FP is the preferred analysis tool when no reference samples are available, right? So you may have heard of this also called a standardless method. It's a really fantastic tool. I love standardless analysis especially when I'm running a number of samples that are just unknown. I don't know what someone will send me a sample and say, tell me what this is and how much is in there. Having standardless protocol is a really nice tool to have. At least kind of points you in the right way. So for a semi-quant approach, it depends, right, on the sample type, approximate values, right? So major, we're about less than 10% weight within 5 to 20% of true value. For minor elements, which is anywhere from like 0.1 to 10% weight, you're usually within about 10 to 30% of your true value. And then if you start thinking about your trace elements, right? So your trace is your 0.1 or less than 0.1% weight, right? You're usually within about 20 to 300% of a true value. So really think of semi-quant. You're going to get much better results with the majors and minors. Trace, not so much. Your accuracy it's limited by unknown concentrations of non-measured elements. These are typically your light elements. The specimen preparation, right? So like, again, we come back to this sample prep of particle size, inhomogeneity, the counting statistics, and the performance of the matrix and the line overlap corrections. So this is the cool part. This is what I like to talk about, the XRF technology itself. So here you see on your screen the XRF product line from Bruker. And Quantum Analytics is a value-added distributor for Bruker AXS. We aligned with Bruker recently, and we did this because we feel that Bruker offers the best-in-class X-ray technology, which it truly matches well with our philosophy here at Quantum. We want to try to have best-in-class technologies, and this works well with our leasing and our rental value add, because we want to make sure if we're leasing out this type of equipment or we're renting out this type of equipment, when it comes back to us and we refurbish the equipment, we know that technology still has very good value, and that's important to us. It's a big part of our business. So looking down the line here, we have a variety of wavelength dispersive, WDXRF, and energy dispersive XRF. Energy dispersive or EDXRF spectrometers are simple and easy to use. They can simultaneously collect signals from several elements and offer resolution from 150 electron volts. Well, with Bruker, they can actually achieve 135 electron volts all the way up to 600 electron volts. With WDXRF, wavelength dispersive XRF, they collect one signal at a time at different angles with the help of a goniometer. These instruments are normally more complex and expensive. However, resolution is considerably higher with these instruments, and they have a range from about 5 electron volts to 20 electron volts. This is the nitty-gritty here. So let's take a minute to just do a comparison of wavelength to energy dispersive spectrometers, because there is a good time to apply one versus the other. And sometimes your application may lend itself to one over the other. So energy dispersive and wavelength dispersive XRF, they're basically the same techniques. They only differ in the way the X-ray spectrum is dispersed. In the case of WDXRF, the X-ray spectrum is dispersed by an analyzing crystal, which is driven internally by a goniometer. A goniometer is like a fancy robotic positioning device, which is usually in conjunction with collimators. In the case of EDXRF, energy dispersive, the crystals and the collimators are absent. X-rays from the sample go directly onto the detector. So the spectrum represents purely a pulse height distribution. As peak position is proportional to the photon energy, it can be used to provide spectral information which elements are present in that sample. The magnitude of the peaks is an indication of the concentration, right? Remember, the peak height is equal to concentration. And so in WDXRF, the crystal separates a certain wavelength, which corresponds to an energy, which on its turn, again, providing information about that element. As such, one energy at a time is being measured. Both energy and wavelength dispersive XRF systems, they may provide primary filters to suppress undesired parts of the spectrum, or they may work to suppress spectral lines, impurity lines, or improve peak to background ratios. So you'll see this as we get into some of the drawings of these instrumentation types, right? So with WDXRF, there are two types or two configurations of collecting spectra. You have sequential and simultaneous. Now, in this discussion, we're not going to dive into simultaneous. We're just going to go today we'll talk about sequential. I think it'll be useful for this discussion. WDXRF, it uses crystals to disperse the fluorescence spectrum into individual wavelengths of each element, providing high resolution and low background spectra for accurate determination of these elemental concentrations. The types of crystals used in WDXRF include minerals, metallic, organic, and some synthetic material layers, right? The WD systems are based on Bragg's law. Many of you probably have heard of Bragg's law. It's a constant in a lot of spectroscopy technologies, right? So this states that crystals will reflect X-rays of specific wavelengths and incident angles when the wavelengths of scattered X-rays interfere constructively. While the sample position is fixed, the angles of the crystal and detector can be changed in compliance with Bragg's law so that the specific wavelength can be measured. Now, collimators are incorporated and further improve resolution by providing different angular divergences to restrict unwanted secondary X-rays from reaching the detector. You have large collimators can be used when high intensity type measurements are favored over resolution, right? Now, the two types of detectors that can be used in a WDXRF instrument, these are, you'll see a couple of different detectors here, and you'll see a sealed proportional counter detector, which are best for measuring lower energies like light elements below iron, while the scintillation detectors are better for measuring higher energies. Now, when we consider energy dispersive XRF, it's designed to analyze groups of elements simultaneously. They all hit the detector all at once, right? So this type of X-ray instrumentation separates the characteristic X-rays from different elements into complete fluorescence energy spectrum, which is then processed for qualitative or quantitative analysis, depending on what you're doing. And these filters that you have in place here are positioned between the sample and the detector, and they're used to improve the signal, reduce the background, and can help focus on certain regions of the spectra that's important to you. So energy, just kind of give you a rule of thumb here, energy dispersive is usually less expensive instrument. It's smaller. It's mechanically simplistic, and the detector is used to detect both energy from the incoming X-rays and intensity from the incoming X-rays. Now, when we think about the range or the elements that can be analyzed by the two different techniques, with a WDXRF, you actually have a little bit more capability here. You're actually able to measure from beryllium all the way to uranium, or if you like the numbers, from 4 to 92. And WD is actually the preferred method usually for light elements and rare earth type samples. Now, if you consider elements that can be analyzed for energy dispersive, we have a couple of different options from Bruker, right? So with the benchtop EDXRF systems, there are two configurations that you have: the the standard X-flash configuration, which gives you elements ranging from sodium to uranium, and with the X-flash LE configuration, which stands for light elements, you get elements that range from fluorine to uranium. So you get a little bit more capability with this configuration. This great thing about energy dispersive, it's very accurate and sensitive to heavy metals analysis. So for those of you that are out in using metals or looking for heavy metals, this is a fantastic tool, but it's definitely not its limitation. It has a wide range of applications that ED is useful for. So maybe this will kind of help give you paint a picture of what's the difference in these resolution capabilities. Energy dispersive resolution is based on the detector capabilities. We talked about that, and like the typical resolution, for these instruments, right? So a standard EDXRF is around 150 for these silicon lithium detectors. The X-flash detector is something that's unique to Bruker that gives you actually even higher resolution. So you get an example for, you measure this at full width half mass for manganese, you are at about, the K alpha is about 1,000 counts per second, right? So that's about 135 there. You got to measure something, and that's what you'll see. It's Peltier cooled. There's no need for liquid nitrogen on this detector, and the resolution is not affected with the increase of the count rate. Now, resolution in WDXRF, it's dependent on the crystal and the collimator that you selected. It's not dependent on the detector like an EDXRF. Typically, WD is about 15 electron volts for manganese at that count rate, right? So it's about 8 to 10 times better resolution than ED with an silicon drift detector, the standard SILI detector. So you get less okay, so why is that great? That's great because you get less spectral overlaps, you get lower background intensity and better detection limits. Okay, so it's a lot of words. Let's look at that from a practical perspective. You see the difference here in resolution of, what is this, copper? Yeah, so if you look, you get better resolution with WD versus ED. I think that's clear here, but with better resolution, you get less spectral line overlap and a more accurate calibration. In a WDXRF, if a spectral line cannot be resolved from the spectral line of interest, then we can try the following to try to resolve that, right? And so we can try to use a different alternate crystal, or maybe we can even use a finer collimator. And in EDXRF, resolution is, again, dependent on the detector itself. You can try to apply some mathematical overlap corrections, you can use filters and all that kind of stuff, but then again, it still comes down to you need a good source of samples and sufficient number of calibration samples if you're trying to do quantitative analysis too, to really identify and quantify these materials. So if we take an example, like a real world example of a steel sample that has been blended with 0.31% of cobalt, and then you analyze it by both EDXRF and WDXRF. Notice that the energy dispersive X-ray peak, it's mostly overlapped by iron, right? So you can't even see the cobalt peak. It's completely masked or overlapped, right? So if you look at this with WD, where you have higher resolution capabilities, you can clearly see and distinguish the two separate peaks of iron and cobalt, and be able to determine and quantitate if that element is present. So again, I kind of like these little comparisons. You have some information about one versus the other. Why do I go with one? What is the differences, right? So with the WD, you have very high precision mechanics. Remember, I talked about the goniometer and the crystal changer, and that is very critical to this type of measurement. You have a higher capital investment, right? These instruments typically cost a bit more, but your precision is better. You have much higher resolution, and you get sensitivities down to the ppm level, but roughly, so it's roughly about 1 to 2 orders more sensitive. It's very fast analysis, and it has very high sample throughput. And conversely, the EDXRF, it's mechanically simplistic, which then, because of that, can make it cheaper. The sensitivities are down to the ppm level. You have very easy handling with the material, with the instrument, and it's smaller, so it can be brought. Samples can be brought, or the analyzer can be brought to the sample, right? So as a benchtop instrument. of all these things here we just talked about, one can say that the analytical performance of an X-ray XRF spectrometer is determined by the range of elements, right? Do you want to go down to beryllium, or is sodium the last element you really need to have measured? Separation of elements. Do you accept less accuracy because the resolution of the peaks is not so well? Maybe you don't need to see that well. Maybe you do. Sensitivity. How much intensity do you get per concentration unit? The peak to background ratio. The better this ratio, the better and lower detection limits. The lower limits of detection. Can you afford to measure? Can you afford the measurement time to go into lower detection limits? Do you prefer a higher power system to obtain higher sensitivity, thus lower limits of detection? And then reproducibility. Do you want the same results today and tomorrow? Again, when you think about this, it really makes it sound like, well, geez, thinking about that, maybe WD is the way I need to go, right? Because it can do all these things. However, that's not necessarily the case. These are all parameters and things that you need to consider based on your type of analysis that you want to run, right? So if you look at the Bruker product line, this is kind of just a good little guideline of why they have these types of analyzers on the market. If you're considering which one or which type of you would need, you'll see that these are kind of some good guidelines, right? So if you look at like this dedicated analyzer here, on the left side is more, these are your energy dispersive X-ray systems. And you can kind of see the guidelines here about 1 to 5 elements with one analyzer, about 5 to 10 elements. But the time for analysis is about 5 to 10 minutes. That's including some sample prep and so on. If you're doing some quick material screening, right, some unknown samples, how long does that typically take in terms of time? You go to WD X-ray systems like the Jaguar and the Tiger. You can run multiple applications on these rather than just a few dedicated applications. You can run a few more elements and relatively around the same amount of time. Depending on what you're running and how many elements you're looking at, they may take more time. But you have more capability on running some more standardless type of analysis, more capability from that perspective. And the timing, even on the full right side with the Tiger, a much faster analysis too, for these standardless types of samples. Now, this is by no means a rigid capability. These are just rule of thumb, basic types of advice on these samples. These instruments can do a lot, and I'm not saying that they're only limited to this. It really is application dependent, but just wanted to kind of give you a rule of thumb and some basic advice. Each instrument has its own unique features, and this is which makes them very suitable for different types of applications, which is why Bruker is offering currently all 4 types of these types of instruments. So a lot of flexibility between these different types of instruments. So I'm often asked the question, well, how much do these instruments cost? And what's the difference in price? Well, typically WDXRF is about 2 to 3 times more expensive than EDXRF. EDXRF is more attractive because of its price, but let's remember here, let's consider we got to choose the right tool for the job, but also be mindful of the fact that new EDXRF technology has improved significantly, and it's especially true for the EDXRF benchtop systems from Bruker. Just because you might currently be using an older WDXRF doesn't necessarily mean that's what you need to continue to use when it comes time for a replacement. Often we can help customers update their lab with a very capable EDXRF benchtop system. This again, it's application dependent. Well, speaking of applications, let's talk about where XRF is being used. It's a tool, well, it's used just about everywhere. You see it in art and antiquities, like for pigments and precious metals, and for cosmetics and things like sunscreen and makeup. You'll see it in chemical, just to analyze their chemical processes. It's very useful for coatings and films, like in paper, foils, metals, glass coatings, all these types of materials. Environmental analysis, so you can analyze soils, sludges, filters, fly ash. In food, you'll see it useful in milk powder, cheese, food, and animal feed. Like metals and ores, you see it in the ores themselves, and the slag, metals, and alloys. And like in minerals, you'll see it in cement and raw materials, petrochemical. You'll see it in the oils and the fuels and distillates, and and the wear metals, and even some of the additives in them. And then in pharmaceuticals, it's a great tool for screening of raw materials. For polymers, you'll see it in plastics, and for doing consumer good inspection, like in ROS analysis. You'll see it in the analysis of pigments of these polymers, the additives in these polymers, and so on and so on. Like uses in agriculture and glass and ceramics. I mean, it's all over the place. So do a little deeper dive in just a few of these applications, and you look at like metals. XRF instrumentation is used to verify the quality and composition of metals used in fabrication to ensure that the final product has good integrity. This analysis prevents incorrect or out of specification metal alloys caused by material mix-ups, incorrect welding chemistry and dilution, or even counterfeit materials from entering a manufacturing process. Special alloys are made by adding expensive elements to steel. XRF is a superior technique that can measure high concentrations of these alloying elements directly in the solid metal. This allows for large cost savings by preventing overuse of the expensive alloying agents. Now for slags, okay, so for those that know slags, this is a byproduct of the metallurgic smelting process. It can contain environmental hazardous materials, and it must be analyzed for environmental composition before it can be reused. You can do, excuse me, gotta go back one. Lost my train of thought. Okay, so this is a quick and reproducible analysis for all oxides in slags. And you can use this to control the slag quality as well as the alloy quality during the smelting process. Now, looking at geology, XRF is employed in geology laboratories to evaluate materials and products with a wide elemental coverage. Now, you get wide concentration ranges and whole varying samples of matrices. It's extensive. Some of these examples will include the analysis of samples at various stages during the mineral processing for quality control and optimization of your recovery rates. XRF has important applications in detecting penalty and waste elements in iron ore that dilute the overall grade of the ore. They change the physical properties of iron and impede the proper operation of the smelting facility. XRF in cement, it's used to perform elemental analysis of cement-making raw materials to ensure concentrations for the major oxides, make sure these are correct. If the raw materials are inappropriate, this is bad. If they're blended improperly, buildings and roads that are made from concrete have poor strength and durability. XRF is a critical part to analyzing this quickly, pretty much throughout the whole process here. Petrochemical, and now I know not everybody that's here, I've seen some of the attendee lists, not everyone here is involved in petrochemical. However, this is a good example how an industry has really embraced this technology for several critical measurements to meet regulatory and quality demands for these types of products, such as the demand for analysis of sulfur in fuels and oils. This is increasing as environmental regulations worldwide continue to tighten. Current fuel sulfur standards in some of the In some countries are already as low as 10 ppm. It's probably going to get lower as we go, and other countries are catching up. XRF instrumentation can achieve these low levels of quantification with excellent precision. XRF is commonly used to validate the formulation of oil additives and also look at the control of wear metals in some of these running processes. Continuing petrochemical, but from an energy dispersive just side of the house, it can handle, again, it can do lots of types of sampling. So you can do solids, loose materials like polymer granules. You can do liquid samples for like fuels and oils. You get a wide range of elements that can be analyzed just in one single measurement. It's fast, and it usually takes just a minute or two. And the sample prep itself is very fast. There's no hazardous acids that are needed to dissolve the sample, no extensive argon gas is needed, and only it's just a small amount of helium for sample chamber purging is used to enhance the performance. Typically, even for a heavy user, one bottle usually lasts weeks. So, but for this type of analysis, a calibration is required. But the good news for you is that the calibration is only needed once, and that's usually during the installation of the instrument. Now for food and some chemical products, these can contain major and trace elements and contaminants which can be detected by XRF. This is exciting because you can do a number of different applications in food. One important application is monitoring nutritional additives to powdered milk. Like milk powder can be measured directly by confirming minerals that are present in the appropriate quantities and the quality for control and compliance of these local regulations. In pet food, knowing the ash content like sodium, magnesium, potassium, calcium oxides, these are all a regulatory requirement. Even knowing like the nutritional additives such as manganese, iron, and zinc. You can screen for heavy metal contaminants or metals in some sort of foreign matter that got contaminated into your food or feed because of the blending or the grinding and mixing up operations in your facility. Oop, one more time. Another great one is, you'll hear this, is counterfeit screening for economically adulterated contaminants and products from foreign countries. This is a hot topic. We're importing foods all over the place. This is a great screening tool to be able to make sure that the food that we eat are safe for us and our animals that we eat. And just going on into snack foods, you got compliance for salt labeling requirements for like chips. I love my chips. Processed meats, cheeses. I love my cheeses. These would be things like sodium chloride, potassium chloride, even calcium chloride. Looking at rice and grains, you can look at the iron and zinc fortification or the trace process metal contamination. Looking at juice, cheese, dairy products, and prepared foods. You can look at calcium fortification and so on and so on. Bakeries, they love to use their titanium oxide as a product brightener. This is a way to get, stuff's not cheap, and so this is a way to make sure that you can get the right concentrations in there. So this is an important part, and really coming up to the last part here, the considerations for this technology, right? Elemental analysis technology it's not just X-ray. There's others that you can use, and you can look here at this graph to kind of show where X-ray fits on there, and see some of the corresponding types of for detection and the sample types that they're capable of running. So you can look here, you got elemental combustion gas analysis, which is great for carbon, hydrogen, nitrogen, and sulfur, even TOC analysis. Obviously our topic today with X-ray fluorescence, arc spark, OES or optical emission spectroscopy, flame atomic absorption spectrometry, graphite furnace atomic absorption spectrometry, inductively coupled plasma, ICP AES or IC is also called as ICP, and ICP-MS, inductively coupled plasma mass spectrometry. For quality and process control, many elemental analysis techniques are available, right? And including XRF, and these are used all across the board in many fields. Now, each of these techniques has several advantages and some disadvantages, which for you to know when to use one and when to apply the other. When the required limits of quantifications are above 1 ppm or non-destructive analysis required, XRF is a very attractive technique. It's one that should really be considered, especially when analyzing solids, powders, slurries, filters, and oils, a wide range of these types of materials. And now, if you look opposed to ICP, AAS, XRF spectrometry does not require sample dilution or digestion, therefore allowing very easy and essentially non-destructive analysis. By avoiding the potential for inaccuracies caused by incomplete dilution and large dilutions, the complete analysis by XRF helps to ensure the accuracy and reliability of these results. Now, there's limitations of XRF, and it's important to know that. So you think about what XRF does, right? And you have some interferences between some of these elements. So being selective is important for your analysis. So there are some high-level elements that may give false positives for another due to overlapping emission lines and limited resolution, right? So there is no info on chemical form of element, right? So you need to have some sort of alternative technique to be able to do speciation. Detection limits. Most use alternative techniques to measure sub ppm levels. Things like ICP, MS is really, or ICP AES, these are great techniques for doing sub ppm type of analysis. And accuracy, XRF is predominantly a surface analysis technique, right? X-rays penetrate only a few millimeters into the sample. To get more accurate results, one must homogenize the samples and calibrate the instrument response using authentic standards. But again, advantages, and these are big ones, guys. So you think about what XRF can do for you. It gives you a large range of applications. It does a lot. It has a huge elemental range from for WD from beryllium to uranium, for ED from effectively sodium to uranium for quantitative. You could do both quantitative and qualitative analysis. It's simple, fast, and safe sample prep without the use of any kind of chemicals. There's no chemical waste, and the analysis is non-destructive on the sample itself. Measurements by XRF are carried out directly on the solid material or liquid with little to no sample prep. The XRF analyzes any type of sample without the need for dilution. We talked about that a bit, but again, I want to kind of hammer that because it does simplify the whole workflow process. Transferring liquids into wet chemical methods from one vessel to another can introduce contamination or loss when using these other techniques. When you're using X-ray, you don't have to worry about that. Also, XRF can eliminate errors that are due to sample inhomogeneity and are easily minimized by using larger sample volumes. XRF can measure gram quantities without any risk of cross-contamination, and therefore can give, there's less error in these types of results. It's a non-destructive technique, right? So the X-ray tube does not produce in an extensive amount of X-ray photons or heat. Therefore, it doesn't damage the sample, and it doesn't change the crystal structure. Irregular shaped samples that fit into the spectrometer can be analyzed without the need for a destructive sample preparation like crushing or grinding. For large samples, the same sample that was analyzed by XRF can later be analyzed using another technique for further investigation if necessary. So maybe you need to have some sort of secondary or further confirmation for investigating, especially like in forensics type studies. One-time calibrations. There's no need to recalibrate daily, people. This is important. This is huge. XRF instruments are very stable over many, many weeks, even months. Daily routine samples. This includes running your control sample, right? Just a daily check to verify both that the instrument and the calibration is working correctly. If there's any change in intensity, that can be corrected by running just a simple and quick drift correction. A knowledgeable person is required for building an empirical calibration, right? This is that calibration curve that you establish. But once that's done, the day-to-day use is simple, and any operator doesn't have to be all that experienced to run an XRF system. So the operator can select the sample, select the position and the application, enter the sample ID, press the button, and get the results. Again, it makes it very simple. My bad. One more time here. I lost my place. Okay, here we go. So there's standby mode. Again, this is just getting analysis run very quickly. Standby mode, it just basically keeps the instrument at a low power. When you're ready to run your sample, you walk right up to it and get ready. You're able to, within a minute, it's warm, less than a minute, it's warm and ready to go at a standby mode, making analysis. At-line analysis is capable at the production site with this type of instrument. A benchtop XRF can go right there at line. Since no liquids or acids or fume hoods are necessary to operate the XRF spectrometer, the instrument can be placed right there at the production facility for easy operation. You get accurate, precise results at very low levels, even sub-ppm is possible, up to 100%. And then ultimately, low cost of ownership. Considering all the initial costs of the instrument and the infrastructure and the running costs of gases, acids, electricity, the waste disposal of some of these other techniques like ICP and AAS, XRF is an attractive instrument. It does not require the use of all those things. It doesn't need to be, therefore doesn't need to be by a fume hood. The only requirement really just electricity, and in some cases you have to use some helium to boost the sensitivity for light elements of the sample. Also, the individual components in XRF spectrometers are not exposed to friction or heat and therefore last for many, many years. Here's an example, like the analysis of liquefied petroleum products or oils, they only require the use of inexpensive disposable liquid cups. Solid samples like metals, they can be measured as is, there's no sample prep. Again, lowering your cost of ownership of that material, of that instrument. So this is the end of my presentation, and thanks for sticking with me. I know we're over the hour here, and I want to thank everyone for your attention. I have a few minutes left for a couple of questions myself. So if you have questions, please take a moment to ask them in the Q&A comment panel now.
Awesome. Oh my gosh, I just feel like I went to XRF school. That was awesome. Thank you so much, Brian. So as you said, we're definitely past the hour, so we have time for a couple of questions, but I know you, Brian and I talked before the webinar, and we said if we did go over, we would be able to, we have documented all the questions that are asked, and we will get back to you with answers to your questions. So even if we don't answer them here, feel free to type them in, and Brian and I will get back to you. So with that, Brian, I'm just gonna ask a couple questions that came in.
Cool.
The first one is, your talk really only discussed laboratory XRF. Does this information apply to handheld XRF too?
Yeah, that's a good question, and I'd say to a degree it does apply, right? And the handheld X-ray systems fall into that energy dispersive category, and yeah, it's a great tool to put in the palm of your hand, go out and do some screening of materials, do quick identification of materials. This is well known in positive material inspection, right? So sorting of recycled materials and things like that. But when you think about accuracy and quantitatively, you just don't have that type of resolution in those handheld units. They have their place, they have their purpose, and they're very useful. But when it comes down to some of these applications that I pointed out, handheld XRF can be limiting.
Awesome. And the final question, and again, if we didn't get to your questions, I have them all written down and we'll get back to you. Um, why is there such a dramatic price difference between energy dispersive and wavelength dispersive XRF instruments?
I mean, we talked about that a bit here in the presentation, and really what it boils down to, there's a lot more involved in an WDXRF than in even just the number of parts that go into that unit. It takes a lot more to align it. It is a very precise instrument, from the goniometer to the crystals that are present, depending on the number of crystals that you have in there, to the collimators and the number of collimators that you have, and so on. It's a very useful tool. However, it can also, because of the complexities of it, um, it also requires some additional um, services and resources for it too. So all that being said, usually warranties is all included into the cost of an instrument too. So um, this person that asked the question they must have tried to be shopping around for an instrument. But the main thing is there are some WDXRF systems out there that are a little bit less expensive than others. So even if you just look at just WDXRF systems, they can range quite a bit within pricing. And again, it comes down to the number of crystals that you incorporate, the number of collimators, and even the protocols or the programs that you put onto the instrument. From an energy dispersive perspective, there's a little bit of gaps between one of those, a low-end energy dispersive to a high-end energy dispersive. And again, that kind of comes down to the detector technology and the sensitivity of it, the the programs that go involved into that instrumentation as well. These are complex instruments. They're not made overnight. They're typically not built on a shelf, just sitting there waiting for someone to go to take them. They're usually made to order, and that's typically why and they're precise and they're very sensitive. So long answer to a short question. I'm sorry, but there's just a lot involved into these types of instruments, and that's why you'll see such a range.
Fantastic. All right. Well, I want to thank everyone for sticking with us. This was a great webinar. Thank you so much, Brian, for presenting today and sharing your expertise. Just for everyone, a reminder, as a registered guest, you'll receive an email within the next, usually we get them out in the next day, the link to the recorded webinar. So you can look back and look at some areas that you may have missed or wanted some extra information on. We have a ton of resources, as you see on the screen. We have a ton of resources on our website, which is www.lqa.com. Make sure to check that out. We've got brochures, app notes, on-demand webinars, and Brian and I are planning our summer webinar series right now. So as we put new webinars on the calendar, you will get emails. So, all right, that's it for us. Everyone, have a great rest of your day.
Thanks, Lauren. Thanks, everybody.
Thanks, Brian.